Hello to everyone. I am Manuel Vincitorio, student in Master Degree Program in Advanced Automotive Engineering at Unimori University. In this video, I'm going to explain the project regarding vibration in a V8 flat plane crank engine that me and my teammates have made within the course of Mechanical Vibrations, held by Professor Francesco Pellicano and Antonio Zippo. First of all, a little overview about what we are going to see during this presentation. We will go through the composition of our team, the problem definition, the theory and the formulation, the numerical implementation with the use of MATLAB software, the results, the conclusion, and the references used. This is our team composition. I am the chairman and the speaker of the group, and then all my colleagues. Milano Gabriele and Micucci Francesco works as a technical developers. Mattetti Lorenzo is our graphics, Basil Sanni is our coordinator, Moroni Filippo is the researcher, and then Messina Simone and Montanari Luca are the numerical developers for MATLAB software. The aim of this project is to study the vibration and the force that is being transmitted by a V8 internal combustion engine with a flat plane crank 60 degrees V angle mounted on the vehicle chassis through 4 mounting points. For do this, the powertrain is considered as a 6 degrees of freedom system with 4 mounting points, modeled as a set of 3 springs and dampers which are sensitive only to axial load and positioned at each corner of the base of the block, which connect the engine to the chassis. Assuming some realistic dimension of a 458 Ferrari V8 from literature survey, a simplified 3D model was generated in Autodesk Fusion 360. Through this project, we will see a mathematical model for the first and second order inertial forces, along with a viscous damped mounting system to carry out a modal analysis and a response of an engine mounted to the chassis. A speed ramp from N1 equal to 0 to N2 equal to 10,000 rpm will be considered. Considering a simplified model, as is possible to see on the left in this short video, for a single cylinder with a crank radius r and connecting rod length L making a crank angle θ, rotating with an angular velocity omega with a reciprocating mass m2, the sum of the primary and the secondary inertial force for the single cylinder reciprocating have this form, where secondary order inertial forces has double frequency and lower amplitude with respect to the primary one. Considering that in a V-twin engine 2 cylinders are connected with common crank and having V angle equal to 2 gamma between these 2 cylinders, the sum of primary and secondary inertial force generated at each bank, right and left, can be calculated, as is possible to see here. With some consideration and substitution is possible to arrive at the expanded equation. The same can be done considering the inertial moments. Lagrange equations have been used in order to derive the equation of motion. In particular, we derive the kinetic energy T and potential energy U along each plane, xy, yz, and xz, where θx, θy, and θz represent respectively roll, pitch, and yaw of the engine block. A, B, C represent the distance from the center of the mass to the 4 mounts in x, y, and z direction. So, define the position of the mounting points with respect to the center of the mass. J represent the elements of the inertia matrix obtained by using 3D software. M represent the mass of the engine block. This equation can be used to find the parameters of Lagrange equation to derive our equation of motion. This is the equation of motion of the system in the matrix forms, where M represent the mass matrix of the system, which have this form. K represent the global stiffness matrix, as is possible to see here, and C represent the global damping matrix, which is the same as the stiffness matrix but changing K with C. Q represent the Lagrangian coordinates, composed by 3 translation, x, y, and z, and 3 rotation, θx, θy, and θz. F represent the applied force vector. As generic viscous damping was used, the global damping matrix C cannot be diagonalized by the modes of the undamped system. Both eigenvalues and eigenvector no longer remain the real field. Duncan approach was used in order to decouple the equation of motion and apply the convolution integral for every modal coordinate eta I. To achieve a stable system, the eigenvalues must not have a non-negative part, with eigenvectors that correspond to complex conjugate of one another. Eigenvectors correspond to the eigenvalues which are not complex conjugate, and they must satisfy the orthogonality relationships. In this analysis, this type of approach is used to define the response of the entire system and to formulate the relationships between the natural frequencies omega n and the frequencies which have a complex part lambda I. The matrix V represents the model matrix. We use this relation in order to, as I said before, decouple the equation of motion and then apply the convolution integral. As we simplify each mounting point as a spring damper system, the forces transmitted to the chassis from each mounting can be found using that equation. The displacement for each mounting is calculated as both the summation of the components because of the translation and the rotation. To calculate this, we have introduced this tensor W with the assumption of little rotation. From this, it's possible to calculate the resultant displacement and the velocities as the derivative of the displacement. In the following slides, the part of the code referred to this section will be analyzed. Initially, we define the mass matrix MM, all the engine parameters, together with the test ramp condition and start and end equal to 0 and 10,000 RPM. xy, yi, and zi represent respectively the absolute position of the four different mounting points with respect to the center of the mass of the engine block. Here we define the inertia, the stiffness, and the damping matrix. As we used genericus viscous damping, we define the transition matrix MT and KT. We calculate both eigenvectors V and eigenvalues D using the MATLAB function EIG. P represents the modal matrix. Then we calculate the natural frequency of the system using this cycle 4. We calculate the total inertial forces in z and y direction in x is equal to 0 and the momentum in x, y, and z direction. Fsim represents the forcing vector. This is the forcing vector. In order to obtain the response of the entire system, we apply the convolution integral at each modal coordinates. We calculate the displacement due to translation and rotation along each axis for one mounting point, the velocity as a derivative of the displacement, and then the force transmitted to the chassis. We use the same approach for the other three mounting points. And then our results. Here on the left it's possible to see our engine block CAD model developed by the use of Autodesk Fusion 360 based on real geometry of 458 Ferrari V8 engine. It's possible to see in a very clear way the position of the four mounting points respect to the entire engine. On the right are shown the graphics regarding the forces and the momentum generated by the engine in a time of 10 seconds, in which the engine speed up from 0 to 10,000 RPM. In particular, it's possible to see a magnification of the forces in this graph, where with a black line it's possible to see the force in x direction, and with the green line and the blue line it's possible to see the force in y and z direction, which are out of phase. And then for the momentum also we have a magnification in this part of the graph, and it's possible to see the light blue line, which is referred to the momentum in x direction, the red line, which is referred to the momentum in y direction, and the dotted orange line, which is referred to the momentum in z direction, and also it is the highest with respect to the other two. In these slides are present the graphics regarding the total displacement and rotation, and the forces transmitted to the chassis by each mounting point. As expected, Both displacement, rotation, and forces increase together with the increasing of the speed of the engine. Forces along x and y direction are less or more in the same order of magnitude of 10 to 15 Newton, and forces along z direction are in order of magnitude of around 2000 Newton. I want to precise that all these values are referred to 10,000 RPM velocity, and as is possible to see in the graphics, all these values decrease a lot if we move to a lower regime of the engine, since they decrease very exponentially with respect to the RPM. They decrease very, very exponentially with a decreasing of the RPM. Here it's possible to see the natural frequency referred to the tree translation and tree rotation and the table regarding the mold shapes. We obtained 12 complex mold shapes because of viscous damping consideration. And then the conclusion. Through this project, we have understood and studied the vibration induced by a V8 flat plane crank in internal combustion engine, simplified as a 6 degrees of freedom. Lagrangian approach was carried out along with Duncan approach in order to study the response of the entire system and the forces transmitted to the chassis. We implemented all these things in MATLAB considering a speed ramp test condition from 0 to 10,000 RPM. This is the list of the references which we have used in order to make this project and to help us. And thank you for your attention.